Hello class, welcome back to the semester. And remember that we were on subtopic 1.5, which is loss of exponents with integer exponents and an introduction to logarithms. And now this is the second part, which is this part, the introduction to logarithms. We already demonstrated the loss of exponents when pertaining to integer exponents, and we already use them in order to simplify things like, for example, this 2 to the 3 times 2 to the 6, that's 2 to the 9. Basically, when we're doing this, we're applying a law of exponents with integer exponents and so on. That's the last thing we did. Okay, so today, guys, we're going to explore the idea or the concept of the logarithm. And today, it's going to be basically completely conceptual. I really want you to understand very well the concept behind the logarithm, because I know that it's it's a scary word. It may be a scary concept because even the word sounds weird. Okay, and I don't know. There's this property of the brain that when the brain looks at a weird word, it already thinks of it as kind of complex. So first, we're gonna take a look at the concept. That's all we're gonna do today. So in order to understand the concept behind logarithm, I want to explain to you the concept of equivalent statements in mathematics or in logic, basically. So what is an equivalent statement? What is an equivalent statement? Well, it's the following. First, let me introduce to you to this new symbol that we're going to use a lot from now on. It's basically a double arrow. I'm going to do it larger in here. It looks like this. Okay, it's a double arrow. And in mathematics, guys, you read this symbol as is equivalent to. That's how you want to read this symbol. Whenever you encounter this symbol in mathematics or in logic, what it means is the following three words: is equivalent to. Okay, pretty much in the same way that just an arrow meant then. Okay, whenever you see this arrow, you need to pronounce it as then. Whenever you see this double arrow, you need to pronounce it as is equivalent. Oops, is equivalent to. Okay, that's how you need to read this symbol. And what is the? How do we use this symbol? We use it when we talk about equivalent statements. I'm gonna give you examples. I'm gonna explain to you what an equivalent statement is by means of examples. The best way to learn. So let's look at this example, guys. Example number 1. 1 plus 2 equals 3. That's in a statement in mathematics. Okay, that's what we know as an statement. All of this thing that I'm enclosing right here, this is what we know as an statement in mathematics. It's basically an affirmation. In mathematics, statements are affirmations. I am affirming right now that 1 plus 2 equals 3. You see? That's a statement. Now, another way, an equivalent way to state the same information between these three numbers is this. It's going to be saying that 3 minus 2 equals 1. This and this, even though they look different, okay, because in here we have a plus sign, in here we have a minus sign, so they look different, but they actually convey the same information, right? 1 plus 2 equals 3 is equivalent to saying that 3 minus 2 equals 1. And we can in fact go from one to the other or vice versa completely, we can do that without any problem. And algebra allows you to do that, right? If we have that 1 plus 2 equals 3, then what you see how I read that? Then we can subtract 2 from both sides and we get this, right? When we subtract 2. So 1 plus 2 equals 3. is basically the same as saying that 1 equals 3 minus 2, which is the statement that I'm saying right here. So these two are equivalent statements. They are equivalent. They carry the same information in different ways. In different ways. Next example. Number 2. It says, all my family members are smaller than 170 meters. All my family members are smaller than 170 meters. That's a statement. That's an affirmation. You see? So all of this is a statement. Now that's equivalent to saying that none of my family members is equal or taller than 170 meters. All of this statement carries the same information as this one, but with different words, with a different perspective, right? Okay, can you see why they actually mean the same? They are equivalent statements. Whether you choose one over the other is completely, it's just a matter of taste, so to speak. But these two are equivalent statements, and that's why I write this double arrow, signifying that this statement is equivalent to this other statement. Number 3, a very simple example. My dog is outside the home. So that's a statement. I'm making an affirmation. Therefore, in mathematics or in logic, that's a statement. My dog is outside the home. So that statement is equivalent to saying that my dog is not inside home. See? Two different things, two different ways of saying the same information. This and this are indistinct from the point of view of logic or mathematics. They are the same. Number 4, a more mathematical example. We have this. A divided by B is equal to C. That's a statement in mathematics. And this statement is equivalent to saying that A equals B times C, right? This and this are the same, exactly the same statements. How can you go from here, from this statement to this statement? Basically, what you have to do is multiply both sides by B, right? And how do you go from this statement to this other statement? What you need to do is divide both sides over B. So this and this are equivalent, and we write that symbol. And a final example. A is greater than B. Another statement in mathematics that's equivalent to saying that B is less than A. If A is greater than B, that's equivalent to saying that B is less or B is smaller than A. So two equivalent statements written in a different way. So that's what equivalent statements are. And that's how you use this symbol. Let's make a small pause and then I'm gonna come back. So with all of this in mind, guys, what does this expression mean? What does the expression logarithm base A of B equals X mean? What does this mean? I'm going to read this for you again. Logarithm base A of B equals X. I know it sounds complicated. You will get it in a moment, believe me. Okay, let's do some experiments, guys. Let's look at this. Look, I'm going to give you for examples, yeah, of the following concept. Look, um, we have this in arithmetic or in algebra. I want you to consider the number 2 as some sort of input, okay? The number 2. And what we want to do to the number 2 is change it or modify it by the application of an operation and a certain number. For example, take the number 2 and we want to modify it by adding the number 3. Okay, I'm going to repeat that. Take the number 2. I want to modify this number, and the way to do that in mathematics is basically you take an operation and another number, and you make that mix, right? You make like, okay, 2 plus 3, oh, that's going to give me 5. So basically, I'm modifying 2 into 5 by the application of an operation, and in this case, this other number, which we may call the modifier. This is not the way it's called. I'm just calling it that way for this purpose, okay? So this is my input, this is my modifier, and this is the result that I have. Very simple statement, right? This is a statement. 2 plus 3 equals 5. Input, modifier, and result. And of course, there's an operation in between. 2 plus 3 equals 5. Okay, now what is the significance of these shapes? Just to represent the input by a yellow circle, and the modifier by a square, and the result by a triangle. They don't really mean anything other than a visual aid. Okay, so all of this is a statement, guys. In mathematics, this is known as a statement. 2 plus 3 equals 5. Now, what is the equivalent statement to this is the following. 5 minus 3 equals 2. Can you see? All of this statement is equivalent to this one. I'm going to give you some seconds to think about that. You see? Basically, the information that this statement and this other statement carry is the same information, but told in a different way. That's basically the idea. All of this statement is equivalent to all of this statement. And what do we have at the end of this second statement, at the end of this process, as a result, so to speak? Well, as a result, what I have here is basically the number that I started with, which is the number 2. You see? So by the application of this equivalent statement, I'm going to the original place, which was the number 2. This was my original input. I modify it by the addition of 3, getting this result, you see? And now with this other equivalent statement, what I'm basically finding is this. With the result of the previous operation, with the result and the modifier, can I get the original input? That's kind of like a question, right? And the answer is yes. All you have to do is get the result, subtract the modifier, and you will get the original input for the first statement, which was the number 2. You see? It's kind of like the reverse process. Okay? Let's continue with more examples. You will understand very well the idea when you see several examples. Now, take the same idea. Take the number 2. That is my original input, and I'm gonna modify it somehow. Now, I'm gonna use the same modifier, the number 3, but now I'm gonna use the operation times. So original input 2 times 3 will give me as result the number 6. 2 times 3 equals 6. Perfect. Very simple. That's a mathematical statement. So far, so good. Now, how can I write this as an equivalent statement, equivalent to statement, in which I'm given the result of the previous statement, which is this one. This is the result. This is the modifier. Okay, and how can I go back to the original input if I'm given this and this? Well, as we know, all we need to do is divide the result over the modifier in order to get the original input, which was the number 2. You see, the number 2 comes in at this point, and we have the same as the result in the equivalent statement. 2 times 3 equals 6 is equivalent to saying that 6 over 3 equals 2. Going back to my original input in the first statement. You see, very simple again. Now, what do you think could be the reason I did not put this one is because I want you to take a guess. Now, we have in here number 2 and then plus 3. So it's addition and the number 3. That was the first example. Now in the second example was the same number, but now with times. 2 times 3 and giving me the result. Now, what other change, what other modification can I do to the number 2 with the number 3? What other operation can we make? If you guessed elevating to the power of 3, you were correct. Okay, so let's raise the number 2 to the power of 3, which I'm gonna put right here. So original input, modifier, in this case the operation is a power, elevating to a power. So 2 raised to the power of 3 is gonna give me the result 8. This is my first statement. And let me write down the equivalent statement using the result, which is 8, and the modifier, which is 3, and taking into consideration that this was raising to a power. So how can I get the number 2? Like, I need to get the number 2 in here as the final result of something in here, something that is going to have the number 8 and the number 3. Take a guess. Well, no, don't guess. It's not a guessing game. Think, what could be this? What could there be in here? Take a guess. Well, no, don't take a guess. Think. If you thought about this, taking the cubic root of 8, that was correct. The cubic root of 8. Okay? That's going to be equal to 2 because the cubic root of 8 is basically the number such that multiplied by itself 3 times gives you 8, which is 2, right? 2 times 2 times 2 is going to give you 8. And therefore, this statement, guys, well, let me write the same symbology. This statement here is the equivalent statement to this one. Okay, and I'm getting, as the result, I'm getting my original input on the first one. Okay, so I believe that by now you're getting the idea, right? By using equivalent statements, we can go back to the original input that I'm having in each of these first statements. You see, as the result in here, I get the original input that I was modifying in the first statements. Perfect. Now we have all the ground laid before us in order to introduce this other concept, guys, the concept of the logarithm. And it works in this way. This is the most important part. Okay, now, what if, same idea, let's take the number 2 as my input. But now, guys, now, instead of having the number 2 as the base of an exponential operation, which is a number elevated to another number, now I'm gonna flip them. I'm gonna put the modifier 3 as the base and the number 2, which is my input, as the exponent. That's the difference I'm gonna make in here. So I'm gonna write the modifier, and now the input, which in these cases was always the number 2, is gonna act as the exponent, not as the base, but as the exponent. You see, this is another way in which I can modify the number 2. You may think, well, no, you're modifying the number 3 because you're raising the 3 to the 2. And you could think in that way too, okay? But you can also think in the other way. You're modifying the number 2 by the application of this operation. What are you doing? You're laying down the number 3 as the base, and you're putting the 2 as the exponent, getting as a result the number 9. 3 to the 2, that's going to be 9, right? So this is my input. This is my modifier, which is going to act as the base, and the input will act as exponent, giving me the number 9. This is a perfectly valid way to change the number 2 into the number 9. Okay, so this is a statement. This is a statement. And here comes the good part, guys. And for most of you, this will be the new concept. We're going to introduce now the equivalent statement to this statement if what you want to find is the exponent. Okay, I want to find the exponent. I want to have the number 2 written in here as a result. Okay, when that number 2 was actually the exponent of an exponential form. You see, in this case, it was this result, the number 2 was the base, but in this case, it's going to be the exponent. And what mathematicians decided to create was this. They said, okay, we're going to say that the logarithm base 3 of 9 is going to be the number 2. And basically what we mean by that is this. Look, what this statement says is this. Logarithm base 3 of 9 is equal to 2 is the same as saying that 3, okay, look at this, 3 to the 2 is equal to 9. These two things are equivalent. I'm going to repeat that several times. Logarithm base 3 of 9 equals 2 is the same or is equivalent to saying that 3 raised to this number, 3 raised to this number, 3 raised to the 2 will give me 9. 3 raised to the 2 is 9. You see? This, guys, is basically the equivalent statement to this statement. It's the equivalent statement that will help you find out, as a result, the exponent in this exponential notation. The exponent, not the base. When you take roots, what you're going to find is the base, guys. But when you take logarithms, what you're going to find is the exponent. The exponent. Okay, so that's basically the definition, guys. The definition of this expression, logarithm base a of b equals x, is this. Let me put this aside. And you need to repeat this so many times, guys, that you memorize this idea. What we mean by logarithm base a of a number b being equal to x, logarithm base a of b equals x, what we mean by this is the same as a raised to the x, a raised to the x being equal to b. A raised to the x is equal to b. A raised to the x is equal to b. And this statement and this statement are equivalent. They are completely equivalent. If sometime later in the future you don't like working with logarithms, you can always go back to the exponential form, which is this one. Because this, let me raise these arrows here. This and this are exactly the same thing, guys. They are exactly the same. They are equivalent. Let me give you more examples. For example, let's raise the number 4 to the 2. What's that going to give me? That's going to give me 16, right? 4 to the 2 equals 16. Well, the equivalent statement of this in logarithm form would be this. Logarithm base 4 of 16 equals 2. This and this are the same. 4 to the 2 equals 16. And logarithm base 4 of 16 equals 2 are the same thing. What this means is that this number, when we raise, well, let me put it this way. When we raise the number 4 to the number 2, we get 16, just like stated in here. Okay? And this is the equivalent statement that will give you the exponent. The exponent of this previous statement, the exponent. Because if you think about this, 4 to the 2 equals 16. If you want to get the base, which is this, if you want to get the base, what you do is this. The square root of 16 will give you the base. Can you see? The square root of 16 will give you the base. But what if you want not the base, which is 4, but the exponent? Well, the equivalent statement is, once again, logarithm base 4 of 16 equals 2. That's going to give you the exponent, because 4 to the 2 equals 16. You see? So basically, guys, what I'm telling you is this. The logarithm is a definition of an equivalent statement of this, so that you can get the exponent, not the base, the exponent. It will allow you to get the exponent. That's all it means, guys. That's all it means. Whenever you have this, a to the x equals b, then if you want to get the exponent, not the base, this is the base. If you want to get the exponent, then the equivalent statement is logarithm base b. No, I'm sorry. I'm sorry. Logarithm base a of b equals x. Why? Because a to the x will give me b according to this. A to the x will give me b. So this statement and this statement are equivalent. And you need to practice that so many times that you get close to perfect memorization of this. So 2 to the 3 equals 8. What is the equivalent statement? Okay, logarithm base 2 of 8 equals 3. 5 to the 3 equals 125. What is the equivalent statement to this statement in logarithmic form? Is going to be logarithm base 5, because that's the base, right? The base is 5. So logarithm base 5 of 125 is going to be 3. Why? Because 5 to the 3 equals 125. You see? That's how it works. And also you need to go backwards. If you know that logarithm base 2 of uh, of 32 is equal to 5, what does this mean in exponential form? Well, it means that 2 to the 5 is 32. So the equivalent statement, get used to the symbol, the equivalent statement to this is writing down 2 to the 5 equals 32. And this thing, all of this statement and this statement have the same information. They are as indistinct as writing this. 1 plus 2 equals 3, being equivalent to 3 minus 2 equals 1. Okay? It's exactly the same. This and this are indistinct from the point of view of mathematics. This and this are indistinct from the point of view of mathematics. I know that your brain sees different words and so on, but from the point of mathematics, they are indistinct. Okay, uh, I'm going to give you the exercises in which you're going to have to go from the exponential form of a statement to the logarithmic form of that statement and backwards from the logarithmic form. Even the words is difficult. From the logarithmic form of a statement to the exponential form, and you're going to do that so many times that you will get very acquainted, very familiar with how you pronounce these things. At least that is the first step. Okay, let me stop it right there. I hope you have understood, and let me take your questions.